So welcome dear students in the class on analog and digital communication. Uh, we will again continue with our topic on amplitude modulation. And in the last class, we had talked about the concept of amplitude modulation. And we had started with various forms of amplitude modulation that we will continue with in today's class. So students, in yesterday's class, if you remember, I had told you what is the meaning of double sideband full carrier. And this double sideband full carrier is the original amplitude modulated signal, which has three components. One is the carrier part, another is the upper sideband part, and third one is the lower sideband part. And then I had told you that in any communication system, there are two important resources. One is power and another is bandwidth. And we want to save these both resources, power as well as your bandwidth. So we don't want to unnecessarily waste these resources. So that's why different forms of amplitude modulation have come up. In those different forms, there are different requirements for power as well as bandwidth. So depending on our requirement, we use that particular form of amplitude modulation. Obviously, we will have to pay price for that. Maybe when we gain advantage in terms of bandwidth or power, in that case, complexity of the system may increase. If we want to keep our system simple, then it may consume more bandwidth, more power. So that kind of trade-off will always exist. Depending on whatever is our main requirement, we go for that form of amplitude modulation. So after double sideband full carrier, as I told you, this is the most simple form of amplitude modulation. Another form of modulation is double sideband suppressed carrier. And I had explained this double sideband suppressed carrier thing yesterday also in detail, and today we will continue with that discussion also. Okay, so in double sideband suppressed carrier, I told you that in short we call it as DSBSC. And important thing that we have to notice here is that in double sideband suppressed carrier we have suppressed carrier. So suppressed carrier means carrier is attenuated. So let us see what is the meaning of this double sideband suppressed carrier. So see, this is the original AM signal where we have three components. One is the carrier one, another is the lower sideband, and third one is the upper sideband. And we have also seen the total power which is used in this simple AM or double sideband full carrier AM. Yesterday also I told you, if we analyze this expression, we have come to know that 2/3 of the total power of AM signal is concentrated in this part, that is your carrier component part. So you can see here that carrier power is 2/3 of the total power of double sideband full carrier AM signal. And after modulation, we have already obtained the lower sideband and upper sideband. So that way our carrier seems to be redundant because we have already utilized carrier in generating our sidebands. So that's why we go after this technique, which we call as double sideband suppressed carrier. So in double sideband suppressed carrier technique, what we do from the original AM signal, we subtract the carrier part, that is VC sin omega ct. We subtract this part. So if we subtract this part, you can very easily observe from this mathematical expression that we are left with only two sidebands, the lower sideband and your upper sideband, and carrier is fully removed. Okay, so this is the concept of your double sideband suppressed carrier technique. So here you can see in the spectrum of double sideband suppressed carrier, that is we have two sideband, one is lower sideband and another is upper sideband, and there is no carrier here. And obviously from this you can make out that the bandwidth requirements remain same as it was in original AM. So the bandwidth requirement is the highest frequency minus lowest frequency, that is twice of FM. but it contains only upper sideband and lower sideband. No carrier is there. The main advantage that we get is the power requirement is less in case of double sideband suppressed carrier. Okay, and if you look at the time domain waveforms, you see once we subtract the carrier part, so then this is 0 and this is the modulating signal. Okay, you can see here that there is no carrier part. If you remember in the initial classes, we had seen our modulating signal like this. It was shifted in the voltage side, but now it has come down after we subtracted the carrier part. Okay, so this is our time domain waveform of the modulating signal, and this is the time domain waveform of the modulated signal. And you can see here that in the modulated signal, the envelope of modulated signal is now touching, you can say, the 0 line or 0 axis. Whereas in case of your original AM signal, it looked like this. So your envelope was looking like this, and your carrier was concentrated between this envelope like this. Whereas in case of your double sideband suppressed carrier, that carrier part has been removed. So in a way, you can say that your envelope has, become compact the way it is low. Okay, so this is the envelope of your double sideband suppressed carrier. And students, yesterday one important point I had told you that you mind the words suppressed carrier. It's not without carrier. In case of double sideband suppressed carrier, we do not fully remove carrier. A small amount of carrier is required in this double sideband suppressed carrier for the synchronization purpose. So we cannot remove the carrier 100%. We require traces of carrier, but the majority of the power that we were consuming in the carrier, that has now been saved. So this is our double sideband suppressed. So I hope it is clear to each and every student. Now let us move forward. So after double sideband suppressed carrier, next form of amplitude modulation is single sideband tech. Okay, so all of you should focus on two things only. One is power and another is bandwidth. In case of double sideband, what we have done, we have saved power, whereas bandwidth remains same. So now one more thing you need to look into, that in case of double sideband, we had two sidebands. One sideband was represented as upper sideband, whose frequency is, say, FC plus FM. Okay, and in the lower sideband, the frequency of lower sideband is FC minus FM. Okay, so in fact, you people should have asked this question. Sir, we had only one modulating signal, whereas the two frequencies in the form of sidebands we have obtained, you can say we have modulating signal present in the two sidebands. Okay, so because FM is present in both lower sideband as well as upper sideband, it means both the sidebands, they carry identical information or the same information. Because of modulation, dear students, you see, let me show you the previous slide. Because of modulation, we have got two sidebands, lower sideband and upper sideband. And these two sidebands, they carry same information. Why same information? Because our modulating signal was one only. We had only one modulating signal, and because of modulation, this modulating signal is present in both the sidebands. Okay, same modulating signal is present in the form of lower sideband as well as upper sideband. So same modulating signal is present in both the sidebands. So if same information is present, then what is the need of sending both the sidebands? So we can think of removing one of the sidebands. Because of modulation, we got three things. One is carrier part, another is upper sideband part, another is lower sideband. Carrier helped us in obtaining sidebands. That's why we thought of removing carrier. Then once we have removed carrier, we are left with two sidebands. Now these two sidebands are also identical. though their frequencies are different, but we are main concerned with the frequency of the carrier signal as well as the modulating signal. Now the modulating signal is common in both the sidebands. Okay, so we can think of removing one of the sidebands also. Okay, and if we remove one of the sidebands, you see here we have removed lower sideband, and in the second figure we have removed upper sideband. So here, if we remove one of the sidebands, then what happens? We are left with only one sideband, that is upper sideband here. Okay, and now because of removal of one sideband, what has happened? The bandwidth requirement has become half. Now, how much is the bandwidth? Bandwidth is highest frequency is FC plus FM, and we have this FC, that is suppressed carrier. Okay, so the frequency bandwidth requirement here is how much? FM. Whereas in case of double sideband suppressed carrier, the bandwidth requirement is 2 FM. So by removing one of the sidebands, we are able to save bandwidth. 50% bandwidth has been saved. So what we will do now, it is in our hands whether we choose LSB or USB. That's up to us. Which sideband do we use? Depending on our requirement, depending on our convenience, we may choose any of the sidebands, and we are able to save the bandwidth. And students, one more thing, apart from bandwidth, in single sideband, we are able to save power also, because now instead of sending both the sidebands, we are sending only one sideband. So power has become further halved. So now in case of single sideband, the power is PC into M square by 4. Okay, whereas in case of double sideband suppressed carrier, it was PC into M square by 2. Okay, so that's why in case of single sideband technique, we have reduced bandwidth requirement and we have reduced the power requirement also. So if mathematically we look into your double sideband signal, it was having the lower sideband and upper sideband, and if we want single sideband, then in case of lower sideband, we will choose this lower sideband only. This is your SSB signal, or we can choose upper sideband. Okay, and how do we obtain these lower sideband or upper sideband? This is how in this block diagram you can see. So first we obtain double sideband suppressed carrier, okay, by using modulating signal and carrier. So we get double sideband suppressed carrier. So we have 2 sideband here and the carrier suppressed. Then by using filter, okay, so by using filter, we can remove any of the sidebands. Okay, so you can filter out either lower sideband or you can filter out upper sideband. I hope this thing is clear to each and everyone. But students, though I am pointing out the more and more advantages, or you can say the benefits that we get in case of double sideband suppressed carrier and single sideband, obviously we are getting advantage, but one price we are going to pay. In double sideband suppressed carrier and in single sideband, in both these techniques, the complexity of the transmitter and receiver is more as compared to simple AM. Okay, the biggest advantage of AM is its simplicity. So whatever is the pure amplitude modulated signal, the biggest advantage is that it is very, very simple. So as we go on, save bandwidth, save power, obviously we are achieving in terms of these two quantities, but obviously we have to pay in terms of the complexity of the signal. I hope all of you have understood this thing. So students, this was the concept of your single sideband technique, and by looking at this block diagram, I hope you are able to understand the concept clearly. Okay, so now after single sideband, there is one another form of amplitude modulation. We call that as vestigial sideband technique. Before I move further into vestigial sideband, in short, we call this vestigial sideband as VSB also, VSB modulation. Okay, and before I explain, let me tell you where do we use this vestigial sideband technique practically. Okay, so in case of your TV transmission, your TV signals, when your TV transmission was, analog in nature earlier. Okay, so in TV signal, we have two things. One is our audio signal, okay, and another is our video signal. Okay, so in case of your TV signal, earlier when our TV were analog, your video signal was transmitted using the amplitude modulation technique, and your audio was transmitted using frequency modulation technique. Okay, just for your information, you may be knowing this thing also. Okay, and in case of video, though we used AM, the form of AM that we used for video signal of TV, that was VSB. So for video, we use VSB AM, VSB form of AM, and VSB means vestigial sideband. Okay, so just now we talked about single sideband, students. So what we had two sidebands earlier. These are the two sidebands. In single sideband, we removed one of the sideband completely, and we were left with only one sideband. Now in vestigial sideband, we do not remove another sideband fully. Okay, what we do, say this is upper sideband. So we keep upper sideband complete. Okay, and the lower sideband, we do not keep complete lower sideband, but only a part of lower sideband. Okay, and this part is called as vestige, and that's why the name of this technique is vestigial sideband. Okay, so in vestigial sideband, what we have single sideband complete plus part of another sideband. Okay, so now this above figure was with respect to upper sideband. If you keep complete lower sideband, then you will keep a part of upper sideband. And these two parts, they are called vestige. Okay, so in case of vestigial sideband, we have one, say, lower sideband, and another is the vestige. Fine. Now, the question arises, why do we do that? Okay, so the answer to that question is that I told you in the previous slide that how do we obtain single sideband? We obtain single sideband by using filter, by using band pass filter at the output of double sideband suppressed filter. Okay, so if our filter is perfect, we will be able to get complete sideband. But my dear students, I explained you in the previous semester also this thing, that our filters are never perfect. Okay, so how do your perfect filters response look like? If you have a perfect filter, your response of the filter looks like this, brick wall type. This is the response of ideal filter. Okay, whereas practically we are not able to have ideal filter, so our response looks like this. This is our, you can say, practical filter. Okay, so if we had ideal filter, we could attenuate our signal at this frequency range, but it's not possible. That's why apart from whatever range we want through filter, some additional part is also coming into picture, and we have to bear with this additional part, because practically in no case we can have ideal filter. We have to survive with non-ideal filter only. So if we have to survive with non-ideal filter, then obviously in pure form, we cannot have that SSB. So in VSB, what we do, we tolerate with, or we send, you can say, small portion of the other sideband also. Okay, instead of completely removing that, and the logic behind that is the use of these practical filters. And the use of vestige also obviously reinforces our signal in some way, and that way the performance of vestigial sideband is better because of this vestige component. I hope this thing is clear to every student. So some portion of the lower sideband or upper sideband, whatever vestige we have chosen, we keep along with other sideband. Okay. So since we keep a portion of the other sideband, what will be the power requirement? The power requirement, this is the power requirement of single sideband, plus this is the power requirement of the fraction of second sideband. F means fraction, some portion, not the complete one. Okay. So this is your vestigial sideband technique. So mathematically, if we look at this is the expression for your double sideband suppressed carrier. So now in case of VSB, this is lower sideband, complete lower sideband, and this is the fraction of upper sideband. And if you take the other way around, then here, this will be, this is your upper sideband. This is your upper sideband, USB. Okay. So in this upper sideband, we have complete upper sideband plus the fraction of the lower sideband. So this is your vestigial sideband. I hope this thing is clear. See, students, maybe you have been able to understand till now that by using such kind of, we are basically trying different ways of our making our signal efficient. If we are facing some problem in any of the form of amplitude modulation, we go for another form, or whatever different options are available with us, we are trying to explore. Okay, our objective is to save the power. Our objective is to save the bandwidth. Simultaneously, our objective is to keep our system as simple as possible. Also, our objective is to maintain the signal quality. It doesn't mean that we will try to save bandwidth power at the cost of the reasonable quality. Okay, so that you have to keep in mind. So we have discussed so far 3 forms of amplitude modulation. One is double sideband suppressed carrier in today's class, then single sideband, then your vestigial sideband. Okay, and there is one more form that is called as independent sideband. Okay, what does that mean? See, this is nothing but this is you can say special case of single sideband only, independent sideband. In single sideband, what we did, we removed one of the sideband. Okay, we removed one of the sideband, and only one sideband was transmitted, carrying information from you can say one user. Whereas in case of independent sideband, both the sidebands will be transmitted, but in both the sidebands, the information will be different. Say LSB will be carrying information of user 1, and USB will be carrying information from user 2. Okay, that's why we call it as independent sideband. Means the 2 sidebands, they are independent of each other because they are carrying information from 2 different users. 2 different users. Okay, so I hope this form of amplitude modulation is clear to everyone. Fine. So let us move forward. So students, these were the various forms of amplitude modulation that we have talked about. Okay, so now let us move forward. Now, after discussing the main concept of amplitude modulation, then amplitude modulated signal, the concept of power, the concept of bandwidth, and different forms of AM, now we move to that how to generate amplitude modulated signal. And students, from the very beginning, I'm telling you that mathematics is very, very important subject to understand engineering subjects. Okay, and for communication also, mathematics will come to our rescue at every point of time. Okay, so we will try to understand things conceptually also. We will try to understand things mathematically also. And after understanding in these ways, then we will move to, you can say, physical systems understanding. Okay, so now we have basically understood what is the meaning of AM. Okay, so now we want to generate AM through some, you can say, system, and we have seen the AM signal. Okay, that in AM signal we have three things present in the complete AM signal, and those three things are your carrier, then your upper sideband, and your lower sideband. Fine. Now the question arises that mathematically, how can we generate that AM signal? Okay, and if you remember that in AM signal, we had mainly two things. If we do not talk about carrier, our information was present in two sidebands. Okay, and these sidebands, one sideband is FC minus FM. Okay, and another sideband is FC plus. This is your AM signal, complete AM signal. Fine. And if you express these two sidebands in the form of sinusoidal expression, then obviously what kind of sinusoidal expression that we come across, you try to recall the expression of AM signal. So what we had there, we had such kind of thing, that is MVC by 2 omega C minus omega m. This is our lower sideband, and MVC by 2 cosine of omega C plus omega. This is your upper side. We want such kind of signal at the output, which is our AM signal. Okay, so the most simple way in which we can obtain this is, we can obtain this through sine omega mt into sine omega ct, means the multiplication of the two sine waves. So if you simply multiply two signals, okay, one signal is your Vm sine omega mt, okay, and another signal is Vc sine omega ct. Okay, so if we simply multiply these two signals, one is your modulating signal and another is carrier signal, we get this form, that is your two sidebands. Okay, so it means the double sideband signal can be directly generated by multiplying your modulating signal and carrier. So what we want a multiplier. Okay, and in order to generate double sideband full carrier signal, we want carrier part also. These are the sidebands. So obviously we need an adder. In that adder, your carrier will be added. And finally, we get the original AM signal, where we have the carrier part, where we have the lower sideband part, and where we have the upper sideband. So if we want to generate amplitude modulated signal, the simplest method is to use a multiplier. Okay, so this is the block diagram, whereby using analog multiplier, which multiplies your modulating signal and carrier, we get the two sidebands, and then we add the carrier as summer at the last, and we get the complete AM signal like this. Very, very simple. I hope this block diagram is clear to every student. So that is the beauty of amplitude modulated signal. That's why again and again I'm telling you that generation of amplitude modulation is very, very simple. How? We simply need to multiply two signals and we get some form of AM. That's it. Okay, so by using analog multiplier and a summer, we can generate double sideband full carrier signal. Fine. So students, this was a simple generation of AM signal using multiplier and summer. Now we look at one more method of generation of AM signal. And again, you will feel that we are, first generating AM signal with the help of mathematics, and then we are using our concept to generate block diagram out of that mathematics. Fine. So now next method to generate AM signal is using non-linear resistance. Okay, so by using non-linear resistance, we can generate AM signal, and we will see how can we do that. If you remember in the previous one, we used one trigonometric identity that if we have some sine A, sine B, then by multiplying two sinusoidal signals, we get cosine of omega C minus omega M, cosine of omega C plus omega. Okay, now let us look at one more technique or method, and that is using non-linear resistance. Okay, I hope all of you are able to understand the meaning of non-linear resistance. We all know the Ohm's law, and what is Ohm's law? V equal to IR. Okay, and this Ohm's law, this is the linear Ohm's law. When we assume that our resistance is linear, then this is the simple Ohm's law, V equal to IR. Whereas practically, you know, your Ohm's law exists in non-linear for non-linear resistances as well. Okay, so this V equal to IR is only for the linear region of the resistance. Okay, so ideally, your characteristic of your resistance, it looks like this. So up to this point, it was linear. Okay, and for the linear portion, your Ohm's law is valid, the way we define it. Okay, and then after that linear region, depending on whether you have positive or negative, you know, your coefficient, or positive or negative resistance coefficient, the corresponding curve is obtained. Fine. So here we are taking non-linear resistance. So obviously we are talking about this curved region. Okay, and if you remember, in our analog electronics, whether we have diodes, whether we have transistors, okay, so there what kind of non-linearity curve we have, those you already know. Fine. So and you also know the difference between the linearity and non-linearity. So when we call a system as linear system, in that case the two quantities are proportional to each other. Okay, the way we have in this Ohm's law, that is V is proportional to voltage is proportional to the current. Okay, and if you know they are not directly proportional, then we call that some non-linearity has come into picture. And when non-linearity come into picture, we get higher order terms, means your second order, third order, and higher powers. Whenever there is a curve, you know, up to the point when we have straight line, we have things up to, you can say, first order. As we move up to second order, third order, you can say non-linear thing come into picture. Okay, and you also know this thing that as we go on increasing the powers, the contribution of their coefficient keep on decreasing. So the maximum coefficient comes from second order power, then third order, then fourth. So for the case of simplicity, and also assuming that maximum contribution comes up to second order, we take this relationship, this non-linear relationship between your current and voltage. Okay, so we take I is equal to A plus BV plus CV square. This is the, you can say, VI characteristic of your non-linear resistance, and this second order term is telling us about the non-linear part. Is that fine? So this A is a constant one. This is your first order term. This is your second. So this point is with regard to non-linear resistance. Now, how to generate AM using this non-linear? This generation means if we pass the two frequencies together, means the two frequencies are passed together through a non-linear resistance. I explained what is the meaning of non-linear resistance. I am passing two frequencies together, means I am passing two frequencies together as a sum, means instead of V, I am passing V1 plus V2. That means the two frequencies are passed together. So instead of V, I substitute V1 plus V2 in this equation. So if I do that, if I further solve it, what do I get? I get I equals to A plus B times V1 plus V2, then C times V1 square plus V2 square plus 2V1. Okay, so this is what I get if I use summation of two voltages instead of the single voltage. Okay, and we know that in case of modulation we need two frequencies or two signal. One is modulating signal and another is carrier signal. So what we do, we take our V1 as the say one frequency, V1 sine omega t. You can assume this as your modulating signal or say carrier signal, and you can assume V2 as your modulating signal. Okay, or let us fix that your V1 is say your carrier signal. This is your carrier signal, fine, and your V2 is say message signal or modulating signal. Fine, and once we substitute the values of V1, V2 in this expression, we get this. So in place of V1, we have taken V1 sine omega t. In place of V2, we have put V2 sine rho t and this one. Okay, and if we further solve this, how come? See, this A is a, what we do, A is a constant term that we have segregated here. Then one more constant term will come. See, just a minute. CV1 square. This expression we have to solve here. V1 square sine square omega t. Okay. I think you are well aware of your trigonometric expressions. That is your what is sine 2 theta. Sine 2 theta is 2 sine theta cos theta. Okay. Two sine theta cos theta. Correct. So similarly, you also know that cos 2 theta. So what is cos 2 theta? It is 2 cos square theta minus 1 or 1 minus 2 cos square theta. Okay, fine. I hope you remember this expression. Then in this third term, you see here, you again have the multiplication of two sine terms, that is sine A, sine B. Okay, so by applying these trigonometric expressions and segregating the terms, what we get, we segregate the constant terms under your terms indicated as 1. Then this is BV1 sine omega t. This is another term that we get. Then BV2 sine rho t. This is another term that we get. Okay, so these are you can say single frequency terms, omega and rho. Okay, then we segregate 2 omega and 2 rho terms. Okay, see here, I told you that your cos 2 theta will be nothing but 1 minus cos. Just a minute. So students, as I told you, your cos 2 theta is equal to 1 minus 2 sine square theta. And from here, you can express sine square theta in terms of cos. That will come out to be 1 minus cos 2 theta upon 2. So this term can be expanded like this in terms of cos 2 omega. Similarly, from this term, you will have cos 2 rho. Okay, so this sine square omega t and sine square rho t, it has given us these two terms. One is your cos 2 omega t and cos 2 rho t. Okay, and that 1/2 part. Okay, so that 1/2 part has come here as a constant. Fine. And then if you look at this point, these are the two sine terms multiplied, sine 2 sine A sine B. Okay, and we already know that it comes out to be as cos of A minus B minus cos of A plus B. And if you substitute the values in place of A and B, we get these terms, term number 5 and term number 6. So if you carefully look at all these expressions, let me erase a few things which are creating confusion. So after putting these frequency values and solving these expressions, we are able to make out few things here. What is this? This constant terms, it means nothing but the DC component, okay, which can be easily removed. Then this sine omega t part, it is nothing but the original signal. We had assumed sine omega t is the carrier one. So this is the carrier part that we can easily filter out. Then we had taken rho as the modulating signal. This is also modulating signal which has come into expression. It can be filtered out. Okay. Then what we have got twice the carrier frequency. That can also be easily filtered out. We have got twice the modulating signal frequency. That can also be filtered out. So our main focus now lies with this one. So here this cos omega minus rho, this is nothing but lower sideband. Okay. And this omega plus rho, this is nothing but your upper sideband. This is what we wanted. So when you pass two frequencies together through a non-linear resistance, then some form of amplitude modulation has been obtained. So now whatever components we desire, those components we can keep with us, and rest of the components we can remove from the resulting signal. So with this, topic, students, I am trying to explain that, here we are taking pure help of mathematics. Okay. And from mathematics, we are trying to generate our lower sideband and upper sideband signals. We are trying to simply generate those things mathematically. Once we are successful in generating those things mathematically, then we give it a physical shape. If you remember in the previous slide, we had talked about multiplication of your carrier and modulating signal. Okay. Now here, what we have tried, you can say, using second order term, okay, in the form of non-linearity of the resistance to generate EMC. Fine. So this is how we generate your AM signal using your non-linear resistance. And I hope all of you are well aware of that, which are the analog electronic devices which you can say, or components which provides us non-linear resistance. Diode is the one best example. So diode provides us non-linear resistance. Your transistor, it provides us non-linear resistance, isn't it? So obviously, if you pass these two frequencies together through a diode, you will get AM. If you pass some of two frequencies through resistance, you will get AM. So we will talk about those things in the next class. So I hope this concept is clear to every student. Okay. Okay, students, then we stop here, and we have concluded our class in well in time. So thank you very much. We stop here.